Hello everyone, this video is about inference for two population means in the case of independent samples. So today we are going to look at how to conduct hypothesis testing for the comparison of two population means, and we'll also see how to construct a confidence interval for the difference between the two population means. The comparison of two population means from independent samples arises when we have one quantitative outcome variable of interest measured from two different groups or populations. Now here there are two types of variables, one quantitative and the other qualitative. The quantitative variable is the outcome of interest, or the variable that is considered as a dependent or response variable, and the qualitative variable is nothing but it is the one having only two categories, or it is a binary variable. Therefore, the two populations or the two groups represent the categories of the binary factor variable or the binary independent variable. So the objective here is to compare the two population or group means of the response variable of interest. We are interested in comparing whether the mean of the quantitative response variable is the same across the two groups or not. So for this purpose, we need to take independent random samples from each group or population under the assumption of a normal distribution. So for the first group or population, a random sample x11, x12, x1n1 could be drawn from a normal distribution with mean mu1 and variance sigma 1 square. Similarly, for the second group or population, another random sample x21, x22, x2n2 could be drawn from another normal distribution with mean mu2 and variance sigma 2 square. So here n1 is number of observations included in the sample of the first group, and n2 is the number of observations included in the sample of the second group. And here mu1 is that of the mean of each observation of the first sample, and sigma 1 square is the variance of each observation of the first sample. Similarly, the mean of each observation of the second sample is mu2, and the variance of each observation of the second sample is sigma 2 square. Then each observation of the first sample comes from that of a normal distribution with mean mu1 and variance sigma 1 square. Therefore, the sampling distribution of the sample mean of the first group is normal with mean mu1 and variance sigma 1 square over n1. Similarly, the sampling distribution of the sample mean of the second group is also normal with mean mu2 and variance sigma 2 square over n2. Therefore, here the interest is to compare the two means mu1 and mu2, or we are interested in testing whether the difference mu1 minus mu2 is 0 or not. So for testing whether the difference mu1 minus mu2 is 0 or not, we could have made some assumptions regarding sigma 1 square and sigma 2 square, which are the variance of the first group and the variance of the second group, respectively. So the first assumption could be the two groups have unequal or heterogeneous variances. Then in that case, sigma 1 square is different from sigma 2 square, or the variance of the first group is different from the variance of the second group. Then in that case, the distribution of the sample mean of the first group will have a normal distribution with mean mu1 and variance sigma 1 square over n1. Similarly, the distribution of the sample mean of the second group will be normal with mean mu2 and variance sigma 2 square over n2. And the second assumption is that the two groups have equal or homogeneous variances. Then in that case, sigma 1 square equals with that of sigma 2 square, or variance of the first group and variance of the second group are the same. Then instead of sigma 1 square and sigma 2 square, we can use simply sigma square in general. Then in that case, x bar 1 will have a normal distribution with mean mu1 and variance sigma square over n1. Similarly, x bar 2 will have a normal distribution with mean mu2 and variance sigma square over n2. Therefore, these are the two different possible cases to be considered in the comparison of two population means in the case of independent samples. So let's consider that when the groups have unequal or heterogeneous variances, then in that case, the distribution of that of x bar 1 is this one, normal with mean mu1 and variance sigma 1 square over n1, and the distribution of x bar 2 is normal with mean mu2 and sigma 2 square over n2. So in that case, the distribution of the difference x bar 1 minus x bar 2 is going to be again normal with the difference mu1 minus mu2 and variance sigma 1 square over n1 plus sigma 2 square over n2. Now this mu1 minus mu2 is nothing but the mean or the expected value of x bar 1 minus x bar 2. And here sigma 1 square over n1 plus sigma 2 square over n2 is the variance of x bar 1 minus x bar 2. So here variance of x bar 1 is sigma 1 square over n1. Variance of x bar 2 is sigma 2 square over n2. Therefore here variance of x bar 1 minus x bar 2 is nothing but variance of x bar 1 plus variance of x bar 2. Using that of the rule of expectation, the variance of x bar 1 minus x bar 2 is nothing but variance of x bar 1 plus variance of x bar 2. So the variance of x bar 1 is sigma 1 square over n1 plus the variance of x bar 2 is sigma 2 square over n2. Therefore here sigma 1 square and sigma 2 square are different. Therefore each variance should be estimated independent of the other. That is, the variance of the first group can be estimated by the sample variance of the first group. Similarly, the variance of the second group can be estimated by the sample variance of the second group. In other words, sigma 1 square is the population variance of the first group. Therefore, it should be estimated by the sample variance of the first group. Similarly, sigma 2 square is the population variance of the second group. It can be estimated using that of the sample variance of the second group. And when we assume that the groups have equal variances, in that case, sigma 1 square and sigma 2 square are the same. So we can denote this common variance by sigma square. So in this case, the distribution of x bar 1 minus x bar 2 will be normal with mean mu1 minus mu2, and the variance now becomes sigma square times 1 over n1 plus 1 over n2. So there is nothing but here we have sigma 1 square over n1 plus sigma 2 square over n2. If sigma 1 square is sigma and here sigma 2 square is sigma, then you have sigma square over n1 plus sigma square over n2. Then this can be written as sigma square times 1 over n1 plus 1 over n2. Now in this case, sigma square is the common population variance of the two groups. So this common population variance is not usually known, therefore it can be estimated using that of the pooled or combined sample variances of both groups. So the pooled sample variance S pooled square is nothing but n1 minus 1 times variance of the first group plus n2 minus 1 times variance of the second group over n1 plus n2 minus 2. Therefore, this pooled sample variance could estimate the common variance sigma square. So instead of its sigma square, we could use that of S pooled square. So the test statistic depends on our assumption whether the groups have different variances or whether the groups have the same variance. Now let's see the steps that we need to follow for conducting hypothesis testing for the comparison of two population means in the case of independent samples. So as usual, first we have to state both the null and alternative hypothesis. So here the interest is whether the two population means are the same or not. So H naught could be mu1 equals mu2. That means the two population means are not significantly different, and the alternative could be mu1 is different from mu2. The two population means are significantly different. So this is the two-sided test. We could have also a one-sided alternative hypothesis test. So in the one-sided alternative hypothesis test, we could have H1 mu1 less than mu2. That is, the population mean of the first group is significantly less than the population mean of the second group, which is a left-tailed test. Similarly, we could have the alternative hypothesis representing mu1 is greater than mu2. That is, the population mean of the first group is significantly larger than the population mean of the second group, and this is as of the right-tailed or right-sided test. Then first we need to state either of these three options, stating that both the null and alternative hypothesis. Second, we need to specify the level of significance alpha, and we have to obtain the critical or tabulated value. Then here, if both the sample sizes or if the number of observations in both groups are large, the critical value should be determined based on that of a standard normal distribution. Therefore, the tabulated or the critical value Z tabulated is obtained as Z alpha over 2 for a two-sided alternative hypothesis or for a two-sided test. So in the case of option 1, here we have a two-sided alternative hypothesis or we have a two-sided test, then the tabulated or critical value should be Z alpha over 2, provided that both sample sizes are large. But if we have a one-sided alternative hypothesis or a one-sided test, which could be a left-tailed test or a right-tailed test, in that case, the critical or tabulated value is obtained as Z alpha. And this Z alpha is nothing but the critical value determined based on the standard normal distribution. And under the assumption that here both sample sizes N1 and N2 are large. Otherwise, if the sample sizes are not both large, the critical value for a two-sided test is going to be determined based on that of a T distribution. So the critical or tabulated value is T alpha over 2 with N1 plus N2 minus 2 degrees of freedom. This is for a two-sided alternative hypothesis or a two-sided test. For a one-sided test, we need to consider that of T alpha with N1 plus N2 minus 2 degrees of freedom. So if the sample sizes are large, we use the standard normal distribution to obtain the critical or tabulated values. But if the sample sizes are not both large, we use that of the T distribution. And if the alternative hypothesis is two-sided, we need to specify the critical value as Z alpha over 2 or T alpha over 2 with N1 plus N2 minus 2 degrees of freedom. And if the test is one-sided, in that case we could consider Z alpha or T alpha with N1 plus N2 minus 2 degrees of freedom. Next, once we obtain the critical or tabulated values, we have to obtain that of the calculated value of the test statistic, or the value of the test statistic that is determined based on that of the data. So again, if the sample sizes are large, we need to use that of the Z test statistic, or that of the standard normal distribution. So the calculated value of the Z test statistic is obtained as x bar 1 minus x bar 2, which is just the sample mean differences of the two groups, minus mu1 minus mu2. This mu1 minus mu2 is actually 0 under the null hypothesis. Here, when we write as mu1 equals mu2, that means mu1 minus mu2 equals 0. Therefore, here the difference mu1 minus mu2 is 0 under the assumption that the null hypothesis holds true. Divided by, in the case of that's of a common variance assumption, here S pooled, that's of the pooled standard deviation times root of 1 over n1 plus 1 over n2. Now this, the denominator part is nothing but it is the standard error of the sampling distribution x bar 1 minus x bar 2. Here we have that of the variance of x bar 1 minus x bar 2 is sigma square times 1 over n1 plus 1 over n2. But sigma square is usually estimated by that of the pooled variance. So instead of sigma square, we replace it by S pooled square. This is the variance. We need to find that of the standard error, or the standard deviation of the sampling distribution x bar 1 minus x bar 2. And that is root of this value, root of S pooled square times 1 over n1 plus 1 over n2. So this root of S pooled square can be taken out from that of the square root as S pooled, which becomes the pooled standard deviation, times root of 1 over n1 plus 1 over n2. Therefore, this will have a normal distribution with mean 0 and variance 1. Similarly, if the sample sizes are small, then we need to use that of the t-distribution. So the calculated test statistic based on the t-distribution is x bar 1 minus x bar 2 minus mu1 minus mu2, which is actually 0 under the null hypothesis, over the pooled standard deviation times root of 1 over n1 plus 1 over n2. Then once we obtain the calculated value and the tabulated value, next we need to make a decision about whether to reject H0 or not. So if the calculated value of the test statistic T calculated or Z calculated, if it is in absolute value greater than that of the T tabulated or the Z tabulated, in that case H0 can be rejected. That means if H0 is rejected, the two population means are significantly different. Or if the p-value is less than that of the specified level of significance, again H0 can be rejected. And based on our decision, finally we need to put a conclusion. Now let's consider an example. Company officials were concerned about the length of a particular drug product retained its potency. A random sample of 8 bottles of the product was drawn from the production line and measured for potency, and a second sample of 10 bottles was obtained and stored in a regulated environment for a period of 1 year. The potency readings obtained from each sample are given below. It says you have the fresh, that's of the drug product, that is taken from the production line, and we have the stored one, which is stored in a regulated environment for a period of 1 year. So here we are asked to test whether the drug product retains its potency. So here we have these two groups, fresh and also the stored one. The fresh is taken from the production line directly, and the second sample is the one that is stored for a period of 1 year. So we are interested in comparing whether the mean potency of the fresh drug products and the mean potency of the stored one are the same or not. So let's denote mu1 as the mean potency of the fresh drug product taken directly from the production line, and let mu2 be the mean potency of the stored drug products that is retained for a period of 1 year. So based on this data, we can obtain these summary statistics. The sample mean of the first group, or the sample mean potency of the first group, or the fresh one, is 10.33, and the sample mean of the second group, or the sample mean potency of the stored drug product, is 9.83. And here the variance of the first group is 0.107, and the variance of the second group is 0.058. Now here there is nothing that is said about the variances between the two groups. Therefore here by default we will consider homogeneous variance assumption, or we will assume that the two groups have the same variance. Then based on the assumption that the two groups have the same variance, we need to obtain that of the pooled sample variance. This pooled sample variance is nothing but n1 minus 1 times sample variance of the fresh drug product plus n2 minus 1 times sample variance of the stored drug product over n1 plus n2 minus 2. So this becomes 0.079. This is also the pooled sample variance. So the pooled standard deviation is nothing but the positive square root of this pooled sample variance. So the pooled standard deviation becomes 0.281. So we already denoted mu1 as the mean potency of the fresh drug product and mu2 as the mean potency of the stored drug product. So the null hypothesis is mu1 equals mu2, which means the mean potency of the drug product taken from the production line is not significantly different from the one that is stored for a period of 1 year. Therefore, if this null hypothesis holds true, that means storing for a period of 1 year doesn't have an effect on losing that of the potency of the drug product. And the alternative is mu1 is different from mu2, which means the mean potency of the drug product taken from the production line and the one that's stored for a period of 1 year are significantly different. Next, let's assume alpha as 5%, and here sample size of the first is 8 and sample size of the second is 10. Therefore both sample sizes are small. We need to use that of the t distribution. So the critical or tabulated value based on the t distribution t tabulated is t alpha over 2 with n1 plus n2 minus 2 degrees of freedom. Why it is alpha over 2? Because here you have a two-sided alternative hypothesis, or we have a two-sided test. So this tabulated value can be easily obtained from a t distribution as 2.12. Then once we obtain the tabulated value, next we need to obtain the calculated value of the test statistic. The calculated value is x bar 1 minus x bar 2 minus mu 1 minus mu 2. This value is actually 0 under the assumption that the null hypothesis holds true, divided by the pooled standard deviation times root of n1 over n1 plus 1 over n2. So this becomes 4.186. Then once we obtain the calculated value of the test statistic and the tabulated value, to make a decision whether to reject H0 or not, we need to compare these two values. So this T calculated, it is 4.186. This is greater than that of the tabulated value, 2.12. So since the calculated value of the test statistic is greater than the tabulated value, then here H0 should be rejected. That means there is sufficient evidence to reject the null hypothesis. Then that means we are in favor of the alternative hypothesis, and we can conclude that the mean potencies of the drug product taken from the production line and the one that is stored for a period of 1 year are significantly different. So the calculated value, which is actually positive, is greater than the tabulated value. Therefore, H0 can be rejected. Or if we obtain the p-value using a certain statistical software, it would be around 0.006, and this value is less than the specified significance level, which is 5% or 0.05. Therefore, again, H0 can be rejected. So our conclusion is there is a significant difference in the mean potency of the drug product taken from the production line and the one that is stored for a period of 1 year at 5% level of significance. And here, in addition, x bar 1 minus x bar 2, 10.388 minus 9.830. This difference is positive. And we have rejected H0. Therefore, since the difference is positive, that means the mean potency of the first group is significantly higher than the mean potency of the second group. Or in other words, the mean potency of the drug product taken from the production line is significantly larger than the mean potency of the drug product that is stored for a period of 1 year. So here we can say that the mean potency of the drug product that was retained for a period of 1 year is significantly lower than the one that is taken from the production line. Yeah. Therefore, that means retaining for a period of 1 year makes the drug product to lose its potency. See the hypothesis testing under the assumption of unequal variances or heterogeneous variances. So in the case of homogeneous variances or common variance assumption, the test statistic depends on that of the pooled variance or pooled standard deviation. So this pooled standard deviation depends on the observations of both groups. But in the case of heterogeneous variances or unequal variances, the variance of each group should be estimated separately. So variance of the first group is estimated by the sample variance of the first group. Similarly, variance of the second group is estimated by the sample variance of the second group. So here the only difference in the hypothesis testing procedures is that of the denominator part of that of the calculated test statistic. So unlike that of the pooled standard deviation times root of 1 over n1 plus 1 over n2, here we have root of s1 square over n1 plus s2 square over n2. So as usual, this will have a normal distribution if the sample sizes are large, but if the sample sizes are both small, this will follow that of a t-distribution. a T distribution with, let's say, V degrees of freedom. Now, in the case of homogeneous variance assumption, the degrees of freedom for the t-test statistic is n1 plus n2 minus 2. Now this is for the homogeneous variance assumption. So this is simple, just the degrees of freedom is n1 plus n2 minus 2. But when we assume the two groups have different variances, the degrees of freedom is going to be, let's say, V, and this V is determined as a function of the sample variances and thus of number of observations of the two groups. So we need to determine V using this formula, which seems something complex. So this V is nothing but just a function of the sample variances. Here we have S1 square, S2 square, and it is also a function of the number of observations. Here we have N1 and N2. So here the denominator should be root of S1 square over N1 plus S2 square over N2. But for the T distribution, we need to obtain that of the degrees of freedom using this function or formula. So this is the only difference. Otherwise, all the other steps that we usually follow for conducting hypothesis testing are exactly the same. So now let's consider this example. A quick but impressive method of estimating the concentration of a chemical in a rat has been developed. The sample from this method has 8 observations, and the sample from the standard method has 4 observations. Assuming different population variances, test whether the quick method gives underestimated results. The data in the two samples are here, it says. So the concentration of the chemical in the rats, here we have the standard method. We have 4 observations, and here we have the quick method, and here there are 8 observations. So we need to compare whether the mean concentration of the chemical between the standard method and the quick method are the same or not. Specifically, we are interested in testing whether the quick method gives underestimated results. So we are interested in testing whether the mean of the quick method is less than that of the mean of the standard method. And the other, here we have given different population variances. Therefore, the test statistic will be the one that is based on that of the estimation of the variances separately, or using this standard error. So let mu1 be the population mean concentration of the chemical from the standard method, and let mu2 be the population mean concentration of the chemical from the quick method. So H0, let it be mu1 equals mu2. That means the means of the concentration of the chemical in the standard and quick methods are not significantly different. And we are interested in testing whether the quick method, that is, whether the second method has a lower mean compared to the standard method. So we need to make this as mu1 is greater than mu2. mu1 is the mean concentration of the standard method, and mu2 is that of the quick method, and we are interested whether this quick method has a lower mean. So we need to write mu1 is greater than mu2. That means the mean concentration of the chemical in the standard method is significantly larger than that of the quick method, or the quick method has a lower mean concentration of the chemical. Then this is a one-sided test, or we have a one-sided alternative hypothesis. Next, let's assume the level of significance as 5%. Alpha is 0.05, and here the sample sizes are small, therefore we need to use that of t distribution. So if we are going to use the t-distribution, this t-distribution under the assumption of different variances, the degrees of freedom is going to be calculated using this formula. So the degrees of freedom becomes around 8. So the tabulated or critical value is t 0.05. Why it is 0.05 instead of 0.05 over 2? Because here we have a one-sided alternative hypothesis. Therefore, this is just T alpha with 8 degrees of freedom. Then you can obtain easily this from a T distribution, which becomes 1.86. Next, we need to obtain that of the value of the test statistic. X bar 1, we need to obtain mean of the first group, or let's say the standard method, and the mean of the quick method, and variance of the standard method, and variance of the quick method. So the mean of the standard method will be 25, and the mean of the quick method will be 21, and variance of the standard method will be 0.67, and the variance of the quick method will be 17.71. Therefore, the calculated value of the test statistic becomes 2.60. Then to make a decision whether to reject or not to reject H0, we need to compare this value with that of the tabulated value. So the calculated value is 2.6, which is actually greater than 1.86. So we have to reject H0. That means we are in favor of the alternative hypothesis. Therefore, our final conclusion is the mean concentration of the chemical in the quick method is significantly lower than that of the standard method. So the calculated value is greater than the tabulated value, H0 can be rejected. Or if you obtain the p-value using statistical software, it will be around 0.0158, which is less than 0.05, therefore H0 can be rejected. So our final conclusion is the quick method gives a significant underestimate results at 5% level of significance, or the mean concentration of the chemical in the quick method is significantly lower than that of the standard method. So now let's consider another example. For a random sample of 120 adult female born in country A, the mean height was 62.7 inches with standard deviation 2.50 inches. For another random sample of 150 adult female born in the country B, the mean height was 61.8 inches with standard deviation 2.62 inches. Under heterogeneous variances, would you reject the null hypothesis that there is no difference in the height between adult female born in the two countries at 1% level of significance? So here we have two groups, that's of country A and country B, and we have the summary statistics. 120 is number of observations for the first group or country A, and the mean height in country A is 62.7 and the standard deviation 2.50. And for the second group or country B, the mean height is 61.8 inches and the standard deviation 2.62 inches. And the level of significance here you have given 1%, and we are required to assume that the groups have different variance. So let mu1 be the mean height of adult female born in country A, and let mu2 be the mean height of adult female born in country B. So the null hypothesis represents mu1 equals mu2. That means there is no significant difference in the mean heights of adult females born in the two countries, country A and B, and the alternative mu1 is different from mu2. There is a significant difference in the mean heights of adult females born in the two countries. And alpha we have already given as 1%, that is 0.01. So here, since the sample sizes are large, particularly we have 120 and 150. Therefore, the sample sizes are both large. We need to use that of the standard normal distribution. So the tabulated value based on the standard normal distribution is Z alpha over 2. Z 0.01 over 2, because here we have a two-sided alternative hypothesis. This becomes Z 0.005 and it becomes 2.58. And next we need to obtain the calculated value of the test statistic. Now, in this case, the variance of each group should be estimated separately. Therefore, the standard error is root of sample variance of country A over N1 plus sample variance of country B over N2. So these are sample mean of the first group minus sample mean of the second group. So the result is going to be 2.88. So 2.88 is greater than 2.58. So that means H0 should be rejected or the test is significant. This calculated value is greater than this tabulated value. So H0 should be rejected. That means there is a significant difference in the mean heights of adult females born in the two countries. So since the calculated value is greater than the tabulated value, then H0 can be rejected or the test is significant. So this is P, that of the P value also can be determined based on that of statistical software, or actually we can obtain this from a statistical distribution of that of the standard normal distribution. The area to the right of 2.88 can be easily found and multiplied by 2. Then the p-value would be around 0.0040, which is less than that of 1%. So again, H0 can be rejected. So if H0 is rejected, we are in favor of this alternative hypothesis. So there is a significant difference in the population mean heights of adult females born in the two countries at 1% level of significance. Specifically, here if we look at 62.7 this is the mean height of adult female born in country A, and this one 61.8, this is the mean height of females born in country B. So 62.7 minus 61.8, this is positive. That means since the test is significant, therefore the mean height of adult females born in country A are significantly larger than that of country B. So we can conclude that the mean height of adult females born in country A is significantly higher than the mean height of adult females born in country B at 1% level of significance. So now let's consider the construction of confidence interval for the difference between the two population means. So the 1 minus alpha times 100% confidence interval for the difference of the two population means mu1 minus mu2 under a common variance assumption is x bar 1 minus x bar 2 plus or minus T alpha over 2 with N1 plus N2 minus 2 degrees of freedom times the pooled standard deviation times root of 1 over N1 plus 1 over N2. And when we assume the population variance are different, in that case, instead of S pooled times root of 1 over n1 plus 1 over n2. Here we need to make root of s1 square over n1 plus s2 square over n2. So this is for the case that the sample sizes are small. If both sample sizes are large, if both are, let's say, greater than or equals to 30, in that case, instead of t alpha over 2 with n1 plus n2 minus 2 degrees of freedom, we need to replace this by z alpha over 2. Similarly, here, in the case of different population variances, instead of t alpha over 2 with v degrees of freedom, we need to replace this by z alpha over 2. So if the confidence interval contains the value 0, that means the difference mu1 minus mu2 equals 0 is not significant. But if the confidence interval doesn't contain the value 0, in that case, we can say that the two population means are significantly different. In other words, if this confidence interval contains the value 0, that means mu1 and mu2 are not significantly different. But if these confidence intervals do not contain the value 0, then in that case we can say these two means mu1 and mu2 are significantly different. So now let's consider one example. Construct the 95% confidence interval for the difference of the population means of the potency of the two types of drugs, the fresh and the stored, considered before. Let me go back to that example one more time. So here we have this, just the mean potency of the fresh drug products that is taken from the production line is this one, and the mean potency of the drug products that is stored for a period of 1 year, this one. So let's construct a confidence interval for the difference between the mean potency of the fresh and the stored drug products. So the sample mean is already obtained there for the fresh drug products. It is 10.388, and the sample mean of the stored one is 9.830, and this 2.12 is that of the tabulated value based on a t-distribution. Yeah, that one. T alpha over 2 is n1 plus n2 minus 2 degrees of freedom because the sample sizes are small. The sample sizes are small, that's 8 and 10. So 0.281, this is the pooled standard deviation of both groups under the assumption that the two groups have homogeneous variances or equal variance. Times root of 1 over 8 plus 1 over 10, then the lower bound of the confidence interval is 0.275 and the upper bound 0.841. Therefore, this confidence interval doesn't contain the value 0. Then we can say that the mean potencies of the fresh and the stored drug products are significantly different at 5% level of significance. Specifically, this confidence interval is greater than 0. The confidence interval is greater than 0. Mean potency of the fresh product minus mean potency of the stored drug product. Therefore, this is greater than 0. That means the mean potency of the fresh drug product is significantly larger than the mean potency of the stored drug product. So from this confidence interval also, we can easily determine that the mean potency of the stored drug product is significantly lower than the one that is taken from the production line, or the mean potency of the drug products that was taken directly from the production line is significantly higher than the one that is stored for a period of 1 year. So in other words, storing the drug product for a period of 1 year makes the drug product to lose its potency. So this is all about today's video. If you have any comments or suggestions, I would like to hear your feedback, so feel free to share your comments and suggestions or anything in the comments box. And if you found this video helpful, please like and subscribe for more. Thank you.